Hello and welcome to this talk on machine learning for microstructure optimization. My name is Steve Kench. I'm a Faraday student based at Imperial College London in the Dyson School of Engineering. So I'm going to start off by talking about why we care about microstructure at all, and then I'll discuss some of the algorithms we've been developing over the last year and how we're looking at leveraging them for optimization. So first of all, why do we care about microstructure? So on the left, you can see an image of a battery, and on the right, you can see the internal microstructure of the cathode of that battery. So a lot of these microstructural features can really strongly affect the performance of our electrode. For example, porosity affects how easy it is for lithium to diffuse into this electrode and integrate into our active material. And that's really strongly related to how fast we can charge and discharge our battery safely. But equally, the more grey active material we have, the more capacity we have because we can hold more charge. So there's often a complex interplay and weigh up between these different properties, whether we want to try and optimize for a given purpose. So before I get into optimization, I just wanted to chat about a bit of background on generative adversarial networks, which are the main tool that we've been using for image processing and generating microstructures. So GANs are a really good machine learning method for taking a real data set and generating fake instances that look like they're from that data set. So for example, they're good at making fake faces, fake images of scenery, and we want to take that powerful tool and apply it in the field of material science for microstructures. Specifically, the first algorithm we developed was about taking that application and extending it so that we could generate 3D volumes from a single 2D slice. The algorithm we developed to do that's called SliceGAN. And the key challenge that it has to face is how do we get around the dimensionality and compatibility between a 2D training set and a 3D volume. And the way we actually do this is we take slices through a generated 3D volume and compare those to the real data set. And that avoids that incompatibility between 3D and 2D, which prevent us from putting those images both into a single neural network. So this allows us to make realistic looking volumes from a single 2D slice. This is really relevant to optimization because 3D volumes are very useful for modeling, but can be quite difficult to obtain because 3D imaging in general is relatively challenging compared to 2D imaging. So we applied this algorithm to a number of different structures. This is a separator that sits between your electrode and your cathode and your anode. You can see on the left is the training image, and on the right is a 3D reconstruction. We can actually make lots of different volumes. This is just a single instance, just like you can make lots of different faces, you can make lots of different microstructures, very large microstructures, in fact, any size you want, which is a very powerful tool for modeling. This is an NMC example. So on the left is the training data. We actually only used a single slice through that, but it's quite useful to compare 3D to 3D. So we took a 3D data set, took a slice through it, and then applied SliceGAN to that. And so on the right, you can see that fake version. On the left, you can see the real one, and they're pretty indistinguishable. And if you want to read more about this, we've just published it in a paper called Generating 3D Structures from a 2D Slice with GAN-based dimensionality expansion. It's available from arXiv, but it's also been published in Nature Machine Intelligence. And it tells you more about some of the statistical comparisons we did to check how realistic those 3D volumes were, and also about some alterations we had to make to the neural networks to make them really applicable for microstructures. So what next? Well, optimization is one of the most important areas in battery science, because as we use batteries for increasingly diverse applications, we have increasingly diverse performance requirements, which means we need to try and tailor those properties, those microstructural properties, to best fit the particular use case that we're looking at. So how can we optimize microstructure for a given case? That's the question. And how can we link manufacturing conditions to those optimal microstructures so that we don't just get left with some idealized microstructure that we can't actually manufacture in reality? What do we need to be able to do that? We need to be able to generate microstructures associated with different manufacturing conditions. We need to be able to extract performance metrics from those microstructures so we can analyze how well they're performing. We need an efficient way to search and find the optimal set of parameters. So I'm going to talk about these three things and the approaches that we've taken for them. The key one is that first one about generating microstructures, because current approaches are very slow. Doing multi-scale physics modeling to generate a 3D microstructure is a very slow approach, as is doing 3D imaging for every time you want to test a new case, when often we want to test hundreds of different manufacturing conditions. So the way that we approach that challenge of generating different types of microstructures is with a conditional GAN. So conditional GAN is similar to what I was talking about earlier, where it's good at emulating realistic data sets, except it has this extra feature in that you can pass your generative adversarial network a label Y. Now, in the case of microstructure, our labels are manufacturing conditions. So in this case, we use compression ratio and binder fraction. So how strongly do you compress your microstructure, and what's the ratio of binder to active material in there? So we obtain these microstructures by doing a few, well, you can see here 9 simulations. A group in France did these simulations for us, Alejandro Franco's group, and once they've done these 9 simulations, we can then teach a GAN to try and emulate that data set. And it works pretty well. So on the right is our fake examples, and on the left is those real ones. And you can see that from left to right, when we look at real microstructures, there's no real correlation between the position of the particles or the position of the binder. Whereas in the fake samples, there's a really strong, when I change the label, the general position of particles doesn't change. Only those features that are statistically different between one sample to the next change. And what that allows us to do is extract just the difference between one sample to the next, only based on the difference in manufacturing conditions, not based on random statistical changes in the position of particles. That's a really useful feature because it allows us to do far less simulations, because we can be relatively certain that the difference in performance from one microstructure to the next is just based on those manufacturing conditions and not based on random statistical variation. So it wouldn't be particularly useful if we could only generate samples that looked like our training set, because we already have those training examples. We already have those 9 training examples. We want to be able to generate everything in between so we can properly explore that space of possible microstructures. And the nice thing about this is you can literally just change the label. So if I train my data with a label of 0 and 1, I can very easily generate a sample with a label of 0.5. So that allows us to interpolate those manufacturing conditions and check what a microstructure halfway between 2 samples that I have looks like, and more importantly, how it would behave. So we can then test all those, we can extract some microstructural features from each of those different microstructures, each generated with a different label, perform some discharge simulations using PyBamm in this case, and this is the results that you get. So you can see that this is a bunch of different, in this case, it's randomly sampled labels discharged at a constant current, I think of 10 amps. And you can see that each of those different microstructures behaves slightly differently because it has slightly different surface area, slightly different tortuosity, slightly different active material volume fraction, and slightly different binder fraction. So that gives us these different performances. And now we just need a way to try and extract the best possible one and to actually efficiently search for that best possible one. And to this end, we can essentially just put a Bayesian optimization wrapper around our generator. So our labels act as these optimization parameters. The properties go into PyBamm, and the resulting performance, so we use accessible capacity, is the property that we're trying to optimize. And in a loop, we successively update and search for the best possible labels for a given, to maximize accessible capacity at a given current. And you can see the results from a number of different currents. So you can see at low current, the optimal structure tends to be highly compressed, so it doesn't get, so high compression gives us big accessible capacity, and that's because it doesn't, the simulation doesn't care so much about tortuosity because we're drawing current slowly. So there's time for those lithium ions to diffuse into the cathode and intercalate, even if most of the electrode is made up of solid active material. Whereas down at 8 amps, when we're trying to draw current really fast, we prefer a lower compression electrode made at lower compression, because we need that extra space so that lithium ions can diffuse into the electrode and intercalate into the material. So in conclusion, compared to conventional methods, conditional GANs are incredibly fast. So the method that we use to generate those real training data sets, those 9 initial microstructures, each of them takes about an hour to make. A conditional GAN takes under a second to make one of those samples. So suddenly we can explore thousands of different types of microstructure in very, very fast compared to those other methods. And one of the nicest things about this is we've connected those initial manufacturing conditions to performance. And last but not least, you could really apply this approach to almost any optimization scenario, whether it's cathode optimization, anode optimization, separator optimization, or really any other type of microstructural optimization where you have a data set of materials generated under different conditions.